Hi there, here is the fourth and last lecture for Chapter 4 notes. So we've talked through solutions in general so far. So characteristics of solutions, what will dissolve, what will dissociate, talked about reactions that occur. Now we're going to look at the concentration of solutions. So there's a few different ways that we talk about and measure concentrations. One that's really common for us is called molarity. So you'll see that right here, and that's where we're going to start. So molarity is one of our main ways of talking about concentration. So in other words, just how strong a solution is. You know, there's strong coffee and there's weak coffee. So that is really an example of molarity. Stronger would have a higher molarity, so it's going to have more solute, or less concentrated has less solute. So here's what the equation for molarity looks like. So we would say molarity, which can be represented by a capital M, is equal to moles of solute over liters of solution. Okay, and it's not a percentage, so we don't multiply by 100 or anything. And as far as the units go, typically our units is this capital M. So like if a solution had a molarity of 2 molar, what that means is 2 moles of the solute would be dissolved in every 1 liter of solution. If it's a 5 molar, then 5 moles have been divided or have been dissolved into 1 liter of solution. You can use moles per liter. It's not as common, but that is a correct unit of molarity as well. So you'll see us use the capital M primarily. So let's talk about how to do this. If we have 0.100 grams of NaCl dissolved in water to make 100 milliliters of solution, what's the concentration of NaCl? So if you see grams, that's the solute NaCl. If you see grams, we can always convert grams to moles, correct? And then our solution is going to have a volume of 100 milliliters, which we can convert to liters. So we'll take our 0.100 grams. We'll go to the periodic table to get our molar mass, which will be 58.44 grams per 1 mole. And let's see what that ends up being. So that gives us 0.00171 moles of NaCl. So that's going to be our top number here in our ratio and equation. And then we'll need to take 100 milliliters and divide by 1,000 to get to liters. So 100 mils, remember, 1,000 milliliters in 1 liter. So that's going to be 0.100 liters. And then to actually find molarity, then we can pick up with those numbers. So molarity is our moles that we calculated divided by our liters. And we get 0.0171 molar. So you see how we just used the capital M? That tells us that many moles of salt of NaCl is dissolved into 1 liter of solution. That's the ratio. Okay, here the next one is talking about molar concentrations of ions. So here you see how it gives me the molarity. So when you see capital M, that's molarity of aqueous solution of calcium nitrate, right? So here what we can do is think about who the substance is. So calcium nitrate is going to be Ca plus 2 and NO3 minus 1. We flippity flop. So we're talking about this guy, right? So what this is telling us is the concentration is 0.025 molar. What it's asking is when this goes into solution and breaks apart into its ions, do you see that you are going to produce 1 calcium and 2 nitrates? Okay, so just think about this. If I put 1 compound into solution, every time I put 1 compound, do you see that I would get 1 calcium and 2 nitrates? So that works for concentration. Every one of these I put in, I get only 1 calcium, so they have equal concentrations, but you're going to have a double concentration of nitrate because you're getting double. So from here, you can see that, oh, your molarity of calcium, which by the way, we might not have run into this yet, these brackets stand for concentration or molarity. That's going to be equal to 0.025. Oops, I put an extra 0. Let's get rid of that. And then nitrate is actually going to be double because you're getting 2 nitrate ions for every compound dissolved. Okay? So that's more a conceptual one than a math one. Okay? Here it says, similarly, what's the molar composition of K plus ions in a given solution of potassium carbonate? So we have K2CO3 would be our solute, our potassium carbonate. Well, we're focusing on K plus. Do you see how you're going to get 2 potassium ions for every 1 compound? So if this is the molarity of the compound, then the molarity of K plus is going to be double that. So 0.030 molar. Okay? Let's look at a couple of different things you might run into here. So here we are asked how many grams of sodium sulfate are required to make 0.350 liters of 0.5 molar Na2SO4. So remember, molarity is equal to moles over liters, right? Okay, so you look for what we know. We know the molarity is 0.500. Do you agree? So I'm going to throw that in for molarity. I know the volume is 0.350 liters. What can I find then? I can find moles. If I can find moles of my solute, I can then convert on over to grams. So I'm going to cross multiply here. 0.5 times 0.350. So my moles will be 1.175 moles of sodium sulfate. And then I can just convert over to grams. So we'll go to the periodic table. We'll go from moles to grams. So I'm going to add up 2 sodiums, 1 sulfur, and 4 oxygens. Okay, so we're just adding up the molar mass, 142.05, and then multiplying it all out, and we get 24.9 grams. What this tells you is, like, if you wanted to make this concentration and you needed 0.350 liters, this is what the lab manager does regularly, you would go get 24.9 grams of the sodium sulfate, right? That's how much solute you need. And then add water until you get up to the desired volume. And then your calculations have done all the hard work and your resulting solution will have this concentration. Okay, so now take a minute, try these kind of on your own. You can pause and stop and pause the video as you go, and I'll have it worked out here for you so you can compare. So here we have molarity. Don't forget to change to liters for the equation. All right, so that's how we work that one. Once again, I recommend stopping and trying on your own, and then you can compare. This one, I'm going to recommend cross-multiplying. Since you're looking for the denominator, this is a common problem algebraically. So if you cross-multiplied, you would first get 0.50 molar times your liters, which you're looking for, equals the 0.038. And then to isolate liters, you would divide by 0.50 and divide by 0.50. So these cancel. So we do this on the side, and that's going to give us liters. So So we're going to get 0.076 liters, and then it actually asks us for milliliters, so we're going to multiply by 1,000, and that'll be 76 milliliters there. Okay? And then one more to look at. What volume, so we're looking for liters, of a 2.50 molar lead 2 nitrate, which is going to be lead 2 nitrate, contains 0.0500 moles of lead. Okay, do you see how there's only one lead in the compound? So we've already talked about this. If this is the amount of lead ions we want, that's the moles, then that's also equal to the moles of the compound, because you see how it's a 1-to-1 ratio? If I put 1 mole of this, I get 1 mole of the ion. If I put 0.05 moles of this, I get 0.05 moles of that. So it's going to be really similar to the last one now. So we have that molarity, we're looking for liters, and we know that our moles are 0.0500 because it's asking for the ion and it's a 1-to-1 ratio in that compound. So we'll cross multiply. You can work through that algebraically one more time to make sure you do it correctly. So we get 0.02 liters. And I think we've got 3 sig figs to work with. All right. Okay, so that's how we can talk about molarity as a unit of concentration for solutions. Now let's talk about how to get the desired molarity through what's called dilution. So if you think about just diluting something in general, that probably brings to mind something like weakening something, adding water. If you're diluting the Kool-Aid down or you're diluting the coffee, you're adding more water, you're weakening it. So what we say for dilution is that you are lowering or decreasing the concentration by adding more solvent, which is generally water for us. So dilution is lowering the concentration by adding more solvent, and I'll put in parentheses water because that's generally our solvent. So we're not touching the solute. You see how, like, say you had salt water? We're adding water. We're not changing the amount of salt at all. So you're not changing solute. You're only changing solvent. You're adding solvent, so the solution volume is getting larger. So the equation for this is M1V1 equals M2V2. What this means is M is for molarity, V is for volume. One side is of the diluted substance and one is of the concentrated. So when you're diluting, you're starting with the concentrated. It doesn't matter which side you have these on. I might should have flip-flopped them, but one side is what you're starting with, your concentrated. The other side is after you've added water, what's the new concentration and what's the new volume. So as volume gets bigger, 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 molarity gets smaller, smaller, smaller because it's getting weaker, okay? You can use any units in these situations as long as they match on both sides, okay? So here it says how many milliliters of 3 molar sulfuric acid, so those have to go on one side, are needed to make 450 mils of a 0.1 molar. So it doesn't matter which side, you've just got to line them up correctly. So on one side, we're going to have 3.0 molar. This is the concentrated one. We're going to look for how much volume we need of it. Then we would add water, because do you see how we are going down in concentration all the way down to 0.10? So we're bringing it from 3 molar, really concentrated, all the way down to 0.10, and we're trying to make a total of 450 mils. When we do the math here, watch what happens with the units. So when we divide by 3.0 molar to get volume alone and 3.0 molar, look at the units. You see how the molar units are going to go away and we're left in milliliters? So that's what our new volume is going to be in. So this all cancels here. The new volume, and we'll talk about what it means, is equal to the math on this side. So 0.1 times 450 divided by 3. We get 15 milliliters. So what does that 15 milliliters mean? It doesn't matter if you can get to the number if it's not helpful, right? What it means is you can take 15 mils of this really concentrated acid, right? That's what you're starting with, just a little bit of concentrate. Add water all the way until your volume goes from 15 all the way to 450. Once you've diluted it from 15 to 450, your new concentration will be 0.1. So you're doing the math ahead of time, so then you know what to do. All right? So here we can do another example. How many milliliters of 5 molar must be diluted to prepare 250 milliliters of 0.10 molar? So really similar. We have 5.0 molar. We're looking for the volume, the new concentration, and the new volume. So you just got to make sure you put things on the right side. So we solve for V1 here. So I take 0.1 times 250 on one side and then divide by the 5, and we get 5 milliliters. And once again, what that means is you're taking 5 mils of the really strong solution, adding water until you get to 250, and you will have weakened it to the desired amount. All right, and then one more. So if 10 mils of a 10 molar stock solution is diluted to 250 mils, what is the new concentration? So we started with 10 molar, and we used 10 milliliters, right? Our new situation is we're looking for the new molarity, and we added water to make 250 mils. So this time we just solve for M2. So we take 10 times 10, right, on one side, and then divide by the 250, and the new concentration is going to be 0.40 molar. Okay. So we use these concentrations when we're doing reactions as well. So we can actually do stoichiometry with reactions that are taking place in solutions. So let's look at how we can apply this to balanced equations. So just as a refresher from last chapter, remember these coefficients in a balanced equation? The 2, the 1, and the 2? Those can always be used as mole-to-mole ratios, right? So if we can get to moles of any one substance, moles of a reactant, moles of a product, we can then hop around the equation. So moles is always your vehicle for hopping between different substances, right? So whenever you're doing these, make sure that you have the reaction written out. You sometimes have to do that on your own. And then make sure you balance the equation properly, okay? Because without that, we can't go between different substances. So what I like to tell students to do is when you have a balanced equation, and this is different than dilution. Do you see dilution up here? All you were doing was adding water. No reaction was occurring. The problems are going to sound very, very similar, but the difference is that dilution only has one substance, right? One solute. Whereas solution stoichiometry, you have a reaction taking place. So don't try to use the dilution equation down here. That equation can only apply really well to dilution. Okay, so here what you'll want to do is kind of keep track of what you have. So how many milliliters of 0.124 NaOH? So I'm just going to list things I know. 0.124 NaOH. I'm looking for milliliters of that guy, right? That's what I got from there. Are required to react with 15.4 milliliters of sulfuric acid that has a concentration of 0.108 molar. Okay, that's the information given, yes? And we know what we're looking for. Well, do you notice that for sulfuric acid right here, you know molarity and you know volume? So what you can do is if you focus on who you know the most about, let's focus on H2SO4 here first. Okay, we know the molarity is 0.108. And we know that we used 15.4 milliliters. So do you notice that with molarity, we can figure out how many moles of H2SO4 were present by using this equation. The liters are going to be 0.0154 liters. So see if you can tell what I've done. I took the milliliters, I converted to liters, I used molarity, plugged it into the equation, and I'm going to find moles of the acid. So I'm only focusing on one part of the equation right now, on the one that I know the most about. So I'm going to cross multiply here, and this is going to give me the moles of acid. Remember, moles are super helpful. Why? They're helpful because that's when I can start hopping between different substances. So if that's the moles of acid, do you see that I can now go to moles of base? What I'm going to do is use the mole-to-mole ratio provided by the balanced equation. Moles of H2SO4 to moles of NaOH. So see, what are my coefficients? A 1 in front of H2SO4 and a 2 in front of sodium hydroxide, yes? So this allowed me to hop over and see how many moles of NaOH I have, which is 0.00332 moles of NaOH. This is almost always going to be 3 steps. Get to moles of somebody. Step 2, hop around from moles to moles. Step 3, focus on the new person you're concerned with, which is NaOH. See how it wants milliliters? So you can set it up 0.124 molar, just like an earlier problem. We know the moles now, and now we can look for liters, right? So we're just using 3 steps, the molarity equation, the mole-to-mole ratio, and back again to the molarity equation. So let's solve this like we did earlier. And we get 0.0268 liters, which is going to be equal to 26.8 milliliters. And that's our answer. That's the milliliters of NaOH that would be needed to neutralize the sulfuric acid perfectly. Because what we did is we figured out how many moles of the acid were present. We hopped over to see how many moles of the base needed to be present. And then we figured out what volume would bring that molar amount. Okay? So let's look at the next. Okay, how many moles of barium sulfate will form if 20 mils of the barium chloride and is mixed with 30 mils of the magnesium sulfate? Okay, so let's just start looking at what we know. Barium chloride, we have 20 milliliters, and it has a concentration of 0.600 molar. The magnesium sulfate is 30 milliliters, and the molarity is 0.500. Okay, this is a different scenario. We actually know exactly how much barium chloride we have and exactly how much magnesium sulfate because we know the concentration and the volume. It wants to know how many moles of this guy will be formed. So what it is it's actually a limiting reactant problem, kind of like last chapter, where I need to figure out how many moles of this do I have, how many moles of this do I have, use the balanced equation, which it is balanced, 2 chlorines, 1 magnesium, everything's balanced, you always want to check, and see how many barium sulfates can be made. So let's do each one to help us. So if we focus on barium chloride first. Okay, we have 0.600 molar. Remember, we always have to get to moles first. Oops, we don't need that. All right, we have, we're going to be looking for moles over the 0.0200 liters. So if we're using molarity equation, we've got to be in liters. So we cross multiply here. So for barium chloride, we have 0.012 moles, right? So now what we can do is take that and hop over and see how many moles of the product we can find, or that we can make. So if I use all of my moles of barium chloride, let's see how many moles of barium sulfate I can make. Do you see how it's a 1-to-1 mole ratio? So it's 0.012 moles of barium sulfate. Okay, that's how much barium chloride could produce, yes? Now we need to do the same thing with the other reactant. So now we're going to focus on MgSO4. Let's see if he could make more or less, right? So we start with the 0.500 molar. We're looking for how many moles of him there are present over the liters, which is going to be 0.0300. So I'll cross multiply. All I'm figuring out is how many moles are present, and it's 0.015 moles. So I used my molarity information to figure out how many moles were present. Now I'm going to use my balanced equation to go from moles of magnesium sulfate to moles of barium sulfate to see how much could be made. It's also a 1-to-1 mole ratio, so it tells me that it's able to produce 0.015 moles of barium sulfate. So if you remember back to last chapter, when you're trying to determine the theoretical yield or the limiting reactant, at the same time, when barium chloride ran out, it could make 0.012. When magnesium sulfate ran out, it could make 0.015. Remember, it's the lesser amount, so we can only make 0.012 moles of barium sulfate because this guy must be our limiting reactant and this guy is our excess reactant. There's not enough barium chloride to make 0.015 moles, okay? All right, let's look at one more here, and then the titration that follows is really going to be very similar. Here it says, how many liters of 0.5 molar HCl are needed to react with 0.10 moles of PbNO3? Okay, here we've got to write out our balanced equation. So we are reacting PbNO3 and HCl. This is going to be a double replacement, so the Pb and the Cl are going to come together. It tells me in the problem I'm making PbCl2 solid, and then the H and NO3 are going to come together to make nitric acid. Should just be aqueous. Okay, then we need to balance it. That's our responsibility. So 2 here for 2 nitrates. There's 2 chlorines, so I'm going to put a 2 here, and that should fix everything. 2 H's, 2 H's, 2 nitrates, 1 Pb, and 2 chlorides. So now I've got my balanced equation. Now you can go add the information that you know about everything, right? So like PbNO3 too. We know that there's 0.100 moles of him present. You see how I got that? We also know HCl has a concentration of 0.500 molar, and we're looking for liters. So the thing you'll notice with these problems is there's some repetition, but also there's differences. So you collect the information you know about each substance, then you just work your way to what you need. So you start with something that's helpful. Well, do you see that we already have moles of this guy? Moles are super helpful because that's when you can hop around. So does it make sense that I can take my moles of lead to nitrate and I can hop over to moles of the HCl? And we'll see why we want that here in just a second. So moles of PbNO3 to moles of HCl, because I need to know more information about HCl, right? This is a 1-to-2 ratio. 2 moles of HCl, 1 mole of PbNO3. So that becomes 0.200. This tells me how many moles of HCl I need, right? So that's the moles of HCl. So if you focus on HCl, you now know molarity and you know moles. So you can now find liters. Watch how that'll work out. So if we focus on HCl, we know 0.500 molar. We know moles now. And now we can find liters. So see how we just used what we had. We went mole to mole, and then we just keep taking steps until we find a route to what we're looking for. So it's going to be 0.400 liters of the HCl. Okay? All right, and then the last section of the chapter is on what's called titration. Titration is going to be using the calculations you already know that we've already talked about, but specifically for when we're taking an unknown solution and finding its concentration. So it's an analytical technique in which one can calculate the concentration of a solute in a solution. So it's just working with solution stoichiometry and determining some unknown component. So here, let's look at these examples, and it's going to look really similar to what we have already been doing. And we will likely have to write out a reaction, okay? So how many grams of NaOH will neutralize 20 mils of 0.150 molar H2SO4? If there are 2 components, you have to deal with the ratio. So you're going to have to write out a balanced equation. Get used to doing the double replacement, right? And flip-flopping charges. We've already done that. So just keep practicing there. And then balance as needed. Okay, so we get our balanced equation. We make sure everybody's ready to go, and then we collect our information. We're looking for grams of this guy. That's what the question's asking for. And we know that we have 20 mils of H2SO4, and we know his concentration, right? So here you just start with where you know something. We don't know anything here. We do know information here. So you start with the molarity to help you. So 0.150 molar equals how many moles of H2SO4 in 0.0200 liters, right? So I'm just using this information right here. I'm cross-multiplying, and I figure out that there's 0.00300 moles of H2SO4 here. Now, once you're in moles, you can hop to whoever you care about. So if I figured out moles of somebody, I can get moles the unknown, which is NaOH. So you use the balanced equation, 1 H2SO4 and 2 sodium hydroxide. And then we actually want grams, so we can just keep going with this one calculation all the way to grams of this guy. So we would add that up from the periodic table, and his molar mass is 40.00. We multiply, and we get 0.240 grams. So that's the amount of sodium hydroxide needed to react fully and neutralize sulfuric acid. Generally, with titration specifically, we're going to be looking for an unknown concentration. But all of these calculations kind of are practice of using solution stoichiometry and a balanced equation. So here, this one's going to be very similar. So I would pause and try to work through it yourself and then compare your work with mine, okay? Once again, we've got to write out a balanced equation, do your double replacement, and then come up with what you know from the problem. Here we find moles of our acid. We can hop over to moles of our base. Okay, so that's our balanced, oops, wrong base. Yep, and use your balanced equation. So 2 to 1. And then we can go one more step from moles to grams of your calcium hydroxide. And I'll add that up. So 1 calcium, 2 oxygens, and 2 hydrogens. All right, and we'll see what it equals up here. 0.0926 grams of your calcium hydroxide is needed to neutralize the acid. Okay. Here, there's going to be a similar scenario. So what's the molarity of sodium hydroxide? See how we're looking for an unknown molarity? If 48.0 milliliters of him is needed to neutralize the 35 mils of sulfuric acid. So we already have seen this balanced equation probably, but we could write it out and balance it. So here we are looking for an unknown concentration. So let's make sure we're all balanced. Okay, and then collect what you know. So we're looking for molarity of sodium hydroxide. We know that it required 48 milliliters of him. to neutralize 0.144 molar of H2SO4 using 35 milliliters of him. So who do you know more about? You know more about the acid, right? So we use our molarity equation to find moles. That's step 1. Then we go mole to mole ratio. And then once we get moles here, we can use moles and volume to find molarity. Okay? Since this is a similar process, I'm going to just give y'all the answer here and you'll be able to work through it and see if you have any questions. So the answer there would be 0.210 molar NaOH. All right, and then the last one, it is using the same balanced equation, same scenario, so I'm going to also give you the answer of that guy. So you can work through these as extra practice and see what questions you have. All right, and that is the end of chapter 4.